Okay, on to talk number 2, API-driven program synthesis for testing static typing implementations, and Thodoris is going to present the work.
Thank you. Hello everyone, I'm Thodoris. I come from Switzerland, and today I'm going to present a work done jointly with colleagues from Switzerland and the UK. This work is about stress testing type system implementation using an API-driven program synthesis approach. Finding bugs in type checkers is an important problem because a type checker is the component in the compiler that ensures whether the input program is correct. Let's see some motivating examples. Here we have a Scala program, and we use the Guava library, a Java library that extends the Java collections framework. Here we create a tuple, and later we access the first element of the tuple, and we call the method retain all, which is defined in the class link-hash multiset. If we give this little program to the Scala compiler, namely Doti crashes. The reason is that if we look at the definitions found in the library, we see that the retain all is defined in a class inherited by link-hash multiset. And as you see here, this superclass has a default access modifier, meaning that this class is not accessible via code outside this package. But retain all has a public access modifier, meaning that this method is accessible by any subclass of this superclass, including link-hash multiset. So although retain all belongs to the API of link-hash multiset, Doti mistakenly treats this method as inaccessible, causing this crash. Here's another motivating example. This time we have a Groovy program. And we call the method removeAll, defined in the arrayUtils class of an Apache library. And we do that in order to remove some elements from the array. When we compile the program, the compiler rejects it with the error message saying reference to method is ambiguous. And if we look to the API of the arrayUtils class, we see that we have a bunch of overloaded methods operating on primitive arrays, and also we have a polymorphic method that operates on arrays of reference types. And although it's clear from the code that our intention is to call the overloaded variant that operates on byte arrays, the compiler thinks that this method is ambiguous and it rejects the program. The issue is caused by a bug in the way the compiler handles variable arguments and arrays of primitive types. So these bugs were detected by approach. So our approach tries to leverage APIs from existing software libraries and synthesize small client program as a way to stress test type system implementations. And we have found more than 80 issues in popular type checkers. Our approach leverages an insight that comes out of a previous bug study published at POPL'24, and this site says that roughly 1/3 of the bug triggering test cases invoke the standard library. They use the collection API, for example. And if we think about it, API-based programs have some benefits. First of all, they provide us with rich feature coverage because libraries are written by experts. They make heavy use of complex features like parametric polymorphism, bounded polymorphism, overloading. So we can easily exercise these features without the need of generating these well-formed definitions on ourselves. And they enable applicability because APIs are available to almost every mainstream programming languages. And since our goal is to synthesize small and self-contained programs, we have efficient testing because now the compiler takes less time to consume smaller programs than larger ones, and also it can potentially facilitate test case reduction because it's easier to reduce a smaller program than a larger one. So the question is, how can we generate interesting client programs? We designed a system called Thalia. So the input of Thalia is an API from the standard library or any other third-party library found in popular software ecosystems like Maven. And the output of Thalia is an oracle that determines the expected behavior of the compiler and the program. And the program is pretty small. It contains expressions that invoke the components of the given API. So in case of a method, the synthesized code contains a simple method call expression. So the first step of Thalia is to encode the given API into a representation called API graph. So nodes in the API graph are either definitions, method, fields, or types. So the meaning here is that we have an edge from a definition to a type that represents the output that stems from the application of the definition. And we also connect a type to definition with definitions. And the meaning here is that in order to call this instance method, we need a receiver of type list. And we gradually build the entire API graph. And actually, this encoding is directly inspired by a very well-known program synthesis paper published at PLDI almost 20 years ago. But we enhanced this encoding in order to support parametric polymorphism. And we do that by adding some labels to some of the edges. And the meaning here is that whenever we have a polymorphic function that returns a polymorphic type, then the target node is the type constructor. For example, here, this node represents the type constructor of list, and the label denotes a type substitution. So the meaning here is that we apply this type constructor to this type substitution in order to get the actual return value of this definition, which is a list of X. So once we have an API graph, how can we systematically explore it? So before answering that, let's introduce another concept called typing sequence. So here we can encode every definition through a sequence of types. So the meaning here is that the first element of the tuple is a type that represents the receiver of the definition. The last element is the expected type that stems from the application of the definition, and any terminal elements represent the parameter. So in our example, for this method, we can encode it using a triple. A is the receiver of this method, B is the parameter type of the method, and B is the output of this method. And actually, a typing sequence represents programs of the following skeleton. And the holes here represent type inhabitants. So the meaning here is that in order to call this method, we need a receiver of type A or a parameter or an argument of type B. And our goal now is to generate well-typed typing sequences for every component found in the API graph, and these typing sequences represent all the possible invocations of a method using different typing patterns. So for this method, we have its signature and three sets. The first set contains the subtypes of the receiver, the second set contains the subtypes of the parameter type, and the third set contains the supertypes of the expected type. And we just take the Cartesian products of these sets and we create different typing sequences. As you see, every typing sequence corresponds to a different test case that invokes our method through using different types. And once we have a typing sequence and an API graph, we introduce a function called gamma, whose output is a concrete expression. So actually, this function gamma fills these holes with concrete expression by finding type inhabitants recursively. And we do that through component-based program synthesis. So finding type inhabitants when we don't have parametric polymorphism is pretty easy. For example, if we want to find the inhabitant of type int, all we need to do is just to enumerate all the paths that lead to this type. Pretty easy. However, when we have parametric polymorphism, the problem becomes much trickier. So in this paper, we introduce an algorithm that is able to tackle this case. I don't want to be too technical here, so I encourage you to read the paper for more details about the algorithm. And here's again the overview of Thalia. We begin with the API graph construction. Then for every component including the API graph, we proceed with the API enumeration, and we produce typing sequences. And then later we concretize the typing sequence into concrete expression written in an IR, and then we employ language-specific translators, and we convert an expression into the IR into concrete source files like a Scala source file, and we give this source file to the compiler and the test, and we check the compiler output for bugs. We evaluated our approach to 3 compilers, Groovy compiler, Conil compiler, and Dotty, and we have found 84 issues, of which 22 have been fixed. 61 were unexpected compile time errors, meaning that the compiler rejects a well-typed program. We have found 6 soundness, 15 crashes, and 2 compilation performance issues. Regarding test case characteristics, the synthesized test cases exercise more than 5 complex typing features, including parametric polymorphism, overloading, higher order functions. And as you see here, that parametric polymorphism, overloading, and functional programming features are the features with the most bug triggering capability, because they appear in all but 8 bug revealing test cases. And the average size of our test cases is between 11 and 30 lines of code. So the key takeaway here is that Thalia can synthesize compact test cases that effectively combine key features for stress testing type checkers. Regarding synthesis time, we are able to handle large APIs with hundreds of classes, thousands of methods, and we are able to handle API graphs with more than 25K edges and synthesize programs in milliseconds. And we also compare Thalia with Iphesus, which is a state-of-the-art framework for testing type checkers. Iphesus follows an approach similar to that of C. Smith. That is, it generates definitions, programs, classes at random and from scratch. And we compare Thalia with Iphesus in terms of test case size and synthesis compilation time, and we saw that Thalia's programs are 1 order of magnitude smaller than that of Iphesus, and in turn this leads to faster synthesis and compilation times, so more efficient testing. We also compare it we compare them in terms of code coverage. The takeaway here is that Iphesus achieves higher coverage because it contains more complex programs with definitions, new classes. So Thalia's programs do not introduce new definitions. They contain just expressions. But the key takeaway here is that despite the reduced size of its test cases, Thalia still explores compiler regions that Iphesus does not reach. And why is that? Because in order to test a new feature with Iphesus, we need to extend the generator in order to generate programs that exhibit this new feature. In Thalia, we don't need to do that. The feature is already there in the given API, and in this way, we can achieve rich feature coverage. And through our analysis, we have found that 22 bugs found by Thalia could not be triggered by Iphesus programs because of that, because of unsupported features. And our evaluation confirms our insights regarding the benefits of API-based programs. So to conclude, we introduced Thalia, an approach that takes an API and produces a small client program in order to stress test compiler implementations. If you want to learn, this is the page of our project. If you want to learn more details, feel free to follow this link. Thank you for your attention.
Thank you very much. Great talk. Any questions from the audience? I have a question. So if I understood right, the sequences that you're generating are effectively boiling down to method calls or things like that, except for these holes where you fill in the things of a particular type. What's the vocabulary of the holes that you fill in? Is it, in the example you showed, it was just a constructor call? Do you support primitive expressions and if-then else's and complex features like that in the language, or is it's mostly just straight line code?
The expressions we use in order to fill the holes are based on the API graph. So they typically are chains of method calls or field accesses, but we also provide constants in order to, because there can be an infinite loop. So up to a certain depth, in order to terminate the synthesis, we generate constants.
Other questions? I have another one. So you compared against your prior work that did random generation, and you spoke about things that Thalia was able to find. Can you say more about what exactly Hephaestus was able to find that Thalia was not?
Mm-hmm. So since Hephaestus generates programs that contain definitions, classes, new functions, Hephaestus programs are able to trigger checks that check the well-formedness of those definitions. So with Thalia, we cannot do that because we just create method calls and
So basically, the standard library is well-formed, and then you're, by construction, generating well-formed sequences of calls to the APIs.
Yeah, the library code is already compiled. The compiler does not need to check the well-formed of the given API.
Okay. Oh, thank you.
You'll have to repeat it.
Yell it, and then we'll repeat it.
My question is, your examples are really small, which is cool. What do you think is sort of the secret of the tool that you're able to find bugs in really, really simple programs? Like, are you doing something, you're using a unique combination of type features in a way the compiler designers didn't expect, or?
Yeah, because if you think
just to repeat the question, so the examples you generate are really small, and you find bugs anyway. Why is that?
Because if we think about it, these APIs contain features like parametric polymorphism, overloading. So in this way, when we have a method call, we are able to trigger the type inference procedures of the compiler and other type-related operations like type substitution, etc. And if we think about it, we don't need to generate very complex programs, right? Because in some sense, type checking is local. I mean, if we have a method call, yeah.
We have time for another question.
We're out of time. Got to switch. But great conversation starter for afterwards. Okay, thank you again very much.